Okay, so this is lesson 1.2, and we're going to talk first informally about the definition of what a limit is. We're going to talk about it graphically, numerically, and then we're going to talk about the formal definition of a limit. So what we're going to do is, this is exactly what I just said, estimate using a numerical graphical approach. We're going to learn different ways that the limit fails to exist, and we're going to study and use a formal definition of a limit, and specifically we're going to use it in the sense of a proof. All right, so introduction to limits. Suppose you are asked to sketch the graph of the function f given by f of x is equal to x cubed minus 1 over x minus 1, where x cannot equal 1, because if not, the denominator is 0. For all values other than x equals 1, you can use the standard curve sketching techniques. So let's go ahead and actually simplify this. All right, so when we simplify the numerator, because we have the difference of cubes, we're going to get this. And now it's clear to see that x minus 1 is going to reduce. Okay, remove the word cancel out from your vocabulary because it did exist. And this is what's stipulating that x cannot equal 1, otherwise the denominator is undefined. And now it's clear to see that we actually have a parabola that is existing, right? And we can put that parabola in standard form. And here it is. Here's our parabola. So now let's actually create the graph, taking into account that I actually have a hole when x is 1 in this function here, I have a hole. So this is what the graph would look like. Okay. So when we actually graph the parabola, excuse this horrendous drawing, okay, this would be our parabola, our vertex. I went ahead and I put this into vertex form. So my vertex is at -1/2, +3/4 here. I have a y-intercept at 0, 1, and I can easily substitute 0 in here. Remember, this was reduced. I get 0, I get 1 squared plus 1 plus 1. If I were to substitute 1 in here, I'm going to get 3 on my output. I'm not substituting the 1 in here because if not, it's going to be undefined. And now it's clear to see that I have a hole here. Okay, so to recap, what we did was we took our function that we're given. We recognized that this was a difference of 2 cubes. So I went ahead and I expanded. Then I noticed that this reduces. This is going to be hilarious. Okay, so then this reduces, and we're going to have x squared plus 1. So it reduces, and what we have now is x squared plus x plus 1. Okay. However, the whole function, technically speaking, is the x cubed minus 1 over x minus 1. That's the original. Even though I can reduce this, therefore I can graph this. And what really happened, so let's go ahead, let's put this into vertex form. That's what I did. I had x plus 1 quantity squared plus 3/4 gives me a vertex here at -1/2. +3/4. Then I'm going to find my y-intercept, substitute 0, and here I get 1. So that's this point here. Use symmetry, and then I went ahead and I graphed the curve. However, because I know that x cannot equal 1, I know that this function must have a hole somewhere. And where does that happen? Let's go ahead and substitute 1 in here. 1 squared, 1 plus 1 plus 1 is 3. So I have a hole at 1, 3. Even though x cannot equal 1, it doesn't. That's what that hole represents. So now let's actually apply that to the concept of a limit. So a limit wants to take into consideration what happens if I approach the graph, that particular point at 1, from the left and from the right. What do I get close to? I'm getting closer and closer as I'm approaching in this direction on the actual curve. I'm approaching the value of 3. So the closer my x values get to 1 from the right and from the left, I'm approaching the value for y, 3. Okay, so more specifically, let's take a look at this table. Okay, as my values start approaching from the right, 1. So let's say 1.5, 1.25, 1.1, 1.01, and it's getting closer and closer to 1. Remember, we cannot equal 1. But the closer and closer I get to that value, take a look at what's happening to your y's. 3.813, 3.31, 3.03, 3.003, question mark. This is technically undefined, but what's happening as we're approaching x from the right, y is approaching 3, or the function is approaching 3, and from the left too. 0.75, 0.9, 0.999, 0.9999, and you can get it closer and closer and closer by increasing the value placement here, 0.99999, and you're going to get closer and closer to 3. So the limit, what we approach, as we approach from the right and from the left, the value for y, that's the answer to the limit. So God bless you, the answer is 3. Okay, here's a nicer picture depicting what we were talking about, right? So we have the closer and closer I get to 1 on x, as x approaches 1 from the left, my value for the function is approaching 3. As I approach from the right, the value is also approaching 3. So although x cannot equal 1, you can move arbitrarily close to 1, and as a result, the function moves arbitrarily closer to 3. So let's use limit notation. This is how we write that. So the limit, this is red, the limit of f of x, so the limit of f of x, as x approaches 1, as x approaches 1, is 3. So one more time, the limit of f of x, or whatever the function is, as x approaches 1, is 3. Okay, so informally, the definition of a limit, if f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. The limit is written as, so the limit of f of x as x approaches c, so whatever value I'm looking at on the x-axis is L. This is the value that I'm looking at on the y-axis. Let's evaluate the function f of x is equal to x over the square root of x plus 1 minus 1 at several points near 0, and use the result to estimate the limit. Let's actually go ahead and create a table. All right, so this is our table that we were looking at. Let's go ahead and find these values. Here we're going to get 1.99499. Here we're going to get 1.3950. Here we're getting 1.4 nines and a 5. So these values are clearly getting closer and closer to 2. Let's take a look and see what happens here. 00499, 2.0050, and there's actually 3 zeros here, 2.00005. So now we can see that we are approaching 2. Here's the graph of the function that we actually just looked at, and here we can clearly see as we approach 0 from the right and from the left, y is 2. So far we've looked at examples where the limit exists. However, there are times where the limit fails to exist, and there are 3 scenarios that we're going to talk about next. So here is the first one. We want to show that the limit, absolute value of x divided by x, as x approaches 0, does not exist. So based on the definition of absolute value, this will give me the piece on the piecewise function that looks like this, right? If x is greater than or equal to 0. It's going to give me the other piece, okay, we're going to pretend it's a nice straight line, if x is less than 0. However, this stipulation tells me not to include 0, so I'm going to change my piecewise function to look like this. So when I graph this, so my second piecewise function, anything divided by itself is a constant value, specifically 1, right? Because if x is 3, x divided by 3 is 1, right? And I'm not allowed to equal, this is 1, and I'm going to have a constant value like this. Same thing with the negative direction, right? I'm going to have -1. I'm going to go in this direction. So here I can see that these two piecewise functions are disjoint. Meaning, if we're taking the graphical approach and I'm approaching 0 from the right, what does f of x equal? 1. Okay, so as I approach 0 from the right specifically, my function equals 1. But if I approach 0 from the left, my function equals -1, and they're not the same. Therefore, the limit does not exist. Okay, so more specifically for the function that we just looked at, this means that no matter how close x gets to 0, there will be both positive and negative x values that are yielding contradictory information. So I was getting f of x is equal to 1 or f of x equals -1. Specifically, if delta, so this symbol is going to be used a lot, so make sure you write that down. The lowercase Greek letter delta is a positive number, then for x values satisfying the inequality, you can classify the values of the function that we looked at as following. For the negative values, we're yielding -1, and for the positive values, we're yielding 1. And here's a formal definition because the function that we just looked at approaches a different number from the right side of 0 than it approaches from the left side. Then the limit for the function as x approaches 0 does not exist. So there are types of behavior associated with non-existence of a limit. This is the first one that we talked about. F of x approaches a different number from the right side of C than it approaches from the left side. Here's another situation. F of x increases or decreases without bound as x approaches C. I'm going to show you a situation where that happens. Or f of x oscillates between two fixed values as x approaches C. Okay, so here's a graph depicting increasing or decreasing without bound as x approaches 0. Specifically, that's going to happen when we have an asymptote. So think of the function f of x is equal to 1 over x squared, where we have vertical asymptote here. Technically, there's also a horizontal asymptote there, right? And as we approach 0 from the left, these values are getting larger and larger. So for instance, maybe I'm getting 1 over 10, or 1 over 100, or 1 over 1,000, or 1 over etc., right? And the same thing's happening in this direction. So there's no specified value that I'm really approaching. It's not like the other graphs that we were looking at where it was clear that we were approaching 3, or it was clear that we were approaching 1, or it was clear that we were approaching a giant gap in the graph, right? Here, it's not clear what we're going to approach, so therefore it fails to exist. All right, so let's take this graph for instance. Let's say we have f of x is equal to sine of 1 over x. So therefore, my values have to kind of be flipped. So instead of pi over 2, it needs to be 2 over pi, so that way when I flip it in this reciprocal function, it is pi over 2, and sine at pi over 2 is 1. At 3 pi over 2, it's -1. And then let's continue that oscillating pattern. 1, -1, 1, -1. Am I approaching a clear value here? No, because it keeps oscillating, it keeps going back and forth between 1, -1. It doesn't matter how close I get to a specified value. Let's say 0. It's going to keep oscillating like this. So it's going to start doing this. And if I were on the x or y axis and I try to zoom in, the more I zoom in, the more oscillations I keep seeing. So it's not clear that I'm approaching a specific value. So therefore, as f of x oscillates between two fixed values as x approaches C, there's no limit. There's no limit that's existing at that specific value.